So this is chapter 3, Understanding the Atom. The chapter starts by looking at some of the environmental concerns plaguing our society currently. One of the biggest concerns, of course, is global warming. Let me tell you a little bit about global warming from my experience on teaching about this phenomena that is plaguing our planet. Back in I think it was 1960, there was a guy by the name of Keeling who was very adventurous in figuring out how much carbon dioxide was in our atmosphere. He actually um, invented a device that measured the amount of carbon dioxide in our atmosphere, and it showed that the amount of carbon dioxide was steadily increasing from about 300 parts per million and to currently 390 parts per million. Why is this important? It's important because for the past 40,000 years, the level of carbon dioxide has been steady at about 300 parts per million for our planet. It's only been the past 50 years that that level has skyrocketed. So here you can see the amount of carbon dioxide in parts per million volume um, on this top chart, and you could see that even in the past 400,000 years, the amount of carbon dioxide fluctuates up and down, and this actually correlates to the ice age and the climate change of the planet for the past 400,000 years. What is interesting is that over here in the past 40, 50,000 years, the carbon dioxide level has been pretty much steady, and it's going up now. So we're actually in the verge of some sort of global warming phenomena, but you can see from this particular chart that it has maxed out pretty much in the past at 300 parts per million. This, by the way, is the temperature correlation of the planet that um, parallels the amount of carbon dioxide in our atmosphere. You can see that in the periods of high carbon dioxide, the average global temperature is high. When there is low carbon dioxide in our atmosphere, the average global temperature is low. And you can see the peaks and valley pretty much parallels the amount of carbon dioxide. Now this is what Charles Keeling measured back in 1965. He measured the amount of carbon dioxide. He actually was out in the California coast, and he measured the carbon dioxide. Here you can see the little fluctuations per year, and that's because this tells you that the amount of carbon dioxide is high during, say, the spring, but it sort of falls off towards the fall right here. So this is the highs and lows of each year, but you can see in general what's going on is that the amount of carbon dioxide is steadily increasing to levels that we've never seen, all the way to about 390 parts per million. And you got to remember, in the past 400,000 years, the amount of carbon dioxide based on ice core measurement has never reached higher than 300 parts per million. So the guy who really is credited for doing this is Charles Keeling, and he actually is a scientist at the Scripps Institute of Oceanography, and he passed away in 2005. But there is an honor um, scholarship that is given to him for him in behalf of him um, at Scripps Institute of Oceanography. So, why is this important in terms of why does the chapter begin with global warming and its cause and effect? It's because in order to understand why carbon dioxide is a key ingredient that causes global warming, you need to understand the atoms that make up carbon dioxide, carbon and oxygen. And so this particular chapter investigates the atoms that make up matter, and so we're going to be taking a look at what exactly is an atom and what are the parts composed of. So back at about 24,000 years, 2,400 years ago, back in when the Greeks were just developing philosophy and understanding more about science, they thought that the matter was basically these four materials: air, water, fire, and earth. These were basically their periodic table. And the history of chemistry and the development of the atom um, spans from about minus 500 BC, that's about 2,400 um, years ago, to our current um, time. And you can see that in the beginning there was a lot of um, speculation as to what matter was, and then there was a dead period in which really not much science was developed until we hit the Enlightenment years. The Enlightenment years saw the development of better understanding of science, better understanding of the world that we live in. And I'm just going to go over some key personalities in this next 10 minutes to help you understand how we are able to understand the model of the atoms today. And it really started with the Greek philosopher, a guy by the name of Empedocles, who was supported by Aristotle, first proposed that the matter was made out of earth, air, fire, and water. And because it made sense to most people, this was the proposal, the hypothesis that was believed for the next 2,000 years. Plus, of course, Aristotle was a pretty big figure back then. And here's an illustration of what they thought was the elements of the universe. A guy by the name of Zeno, it's about 400 BC, thought, and also supported by Aristotle. Aristotle supported a lot of people, but he thought that matter could be infinitely divisible. What does this mean? It means that you can take a piece of rock, split it in half, and keep splitting it in half, and keep splitting it in half, and you will never reach an end. So it can be infinitely divisible. It's like taking a number and dividing it by 2. You can never reach the end, because whatever number you pick, even if it's a small number, you can still divide by 2. So there's really no end. That's the concept that they proposed in terms of matter. So here's an illustration of that. Leucippus and Democritus were the first really to propose the idea that matter was made out of some indivisible. What indivisible means is not invisible, but indivisible. It means that it can't be divided into smaller parts. And it was an atheistic belief, but they believed that atoms that make up, and he coined the term atoms, that make up matter had different types of shape. Water atoms, for example, had smooth surface. That's why it felt subtle and refreshing, whereas fire atoms had sharp edges. That's why it hurts when you touch it. So that was what was proposed by Democritus and Leucippus, and these guys pretty much went unnoticed, just because nobody really could understand how you could have these small pieces of matter be responsible for everything we see. So the idea of earth, air, fire, and water was what was carried on for the next 2,000 years. So the book illustrates the idea of an atom by taking a look at the sand from a faraway distance. It looks like it's a continuous type of terrain, that it's one continuous piece of substance. But if you look really closely, you can see that it's actually made up of very, very small fine grains. And that's what Democritus proposed. If you look really closely on anything, it's made out of very, very fine particles called atoms. And so for the next 2,000 years, people believed that matter was earth, air, fire, and water. And so with that belief, they thought that they can take any material and convert it to something else. And that, of course, gave rise to the alchemist who was trying to convert lead into gold. And of course, that never happened. But one thing that did develop out of that was the laboratory notebook, because a lot of these alchemists were making such huge mistakes and were being beheaded by the king that they started to document their work so that they wouldn't repeat their mistakes. A guy by the name of Roger Bacon, actually a clergyman, actually did experiments, and he was able to write down meticulous notes, and it was through experimental procedures and documentations that he showed that he discovered many things, that rainbows, for example, were based on the water droplets, the sun reflecting off the water droplets. So Roger Bacon really started to have people think about doing some sort of scientific experiment, some sort of objective experiments to answer questions. But he was back in 1250 AD. A priest by the name of Pierre Gassendi actually said that atoms were created by God. And because he put this out there, people were now able to explore what atoms were or what matter was without retribution. And so that actually helped in the Enlightenment years to question the Greek hypothesis of matter. It really started with Robert Boyle. He did a lot of experiments with gases, and he performed detailed experiment, and he showed that atoms weren't really earth, air, fire, and water, that you can get a fundamental piece that you couldn't break down any further. So he started to give credence to Democritus and break down earth, air, and fire and water model of matter. A guy by the name of Antoine Lavoisier, who lived in the French Revolution era, actually is our father of modern chemistry. He did meticulous work in which he showed that matter can't be created or destroyed, only converted from one form on the other. That's the law of conservation of mass. And he's given credit for a lot of achievement, unfortunately, because he lived in the era of the French Revolution, and he helped pay for his experiments through being a tax collector. He had an unfortunate end of being beheaded by the Frenchmen. So he, one of the experiment he did was he took some piece of paper, he burned it, and he showed that by burning it, that the ashes were lighter than the original piece of paper. But when he burned it in a chamber in which the gas was collected, showed that the ashes and the gas was no heavier or lighter than the original piece of paper. So he did a lot of experiment in that sense. This is a little video snippet of Lavoisier and
Monsieur, it is my great ambition to demonstrate that nature is a closed system, that in any transformation, no amount of matter, no mass, is ever lost, and none is gained. Over here, please. This precise amount of water is heated to steam. This steam is brought into contact with a red-hot iron barrel embedded in the coals. From this end, we cool the steam. But interestingly, we collect less water than we started with. So clearly, we lose a certain amount of water. However, we also collect a gas, and the weight of the iron barrel increases. Now, when we combine these two increases, the new weight of the iron barrel and the gas we have collected, they are exactly equal to the weight of the lost water.
Ah, but is it atmospheric air, Monsieur Lavoisier?
No. No, because I am measuring it to the very last grain. I can see that it is lighter than the air around us. And, moreover, it is flammable. Voila.
Water is made out of hydrogen and oxygen. So what he had done is get the oxygen to stick to the inside of a red-hot iron rifle barrel. He was basically just making rust, which is oxygen and iron, but he was making the rust really quickly. Now that left the hydrogen, what he called combustible air, and that was just floating around as a gas. No mass had been lost, it had merely been transformed. And now he wanted to transform it all back into water.
This is only the beginning. In the next few months, I hope to demonstrate that I can recombine this combustible air with vital air and transform them both back into water. I will recreate exactly the same amount of water that was lost here in this process. It is my hope to complete the cycle, water into gas, into water, and not a drop lost.
For a long time, Lavoisier had suspected that the exact amount of matter, the mass, involved in any transformation was always conserved. But to prove this, he had to perform thousands of experiments, and he had to do the measurements with incredible accuracy. That's where his great wealth from being a tax collector came in. He could afford to commission the most sensitive instruments ever built. He became obsessed with accuracy.
Expose this persecutor of yours.
For years, the Lavoisiers burned, chopped, melted, and boiled every conceivable substance. They'd shown that as long as one is scrupulous about collecting all the vapors, liquids, and powders created in a transformation, then mass is not decreased. Liquids might become gases, metals may rust, wood may become ash and smoke, but matter, the tiny atoms that make up all substances, none of it is ever lost. The crowning glory of this opus was their remarkable use of static electricity to cause oxygen and hydrogen to recombine back into water.
So you see, that was the development of the law of conservation of mass. The woman in that video series was his wife. That's a video clip that you could look up, and it showed the history and life of Antoine Lavoisier. Another person by the name of Joseph Strauss proposed the law of definite proportion, or law of constant composition. This law simply states that matter is combined with a certain ratios of atom. That water has 2 hydrogens and 1 oxygen. If you want to do it by mass, then the mass ratio of hydrogen to oxygen is 1:8. If you have something else that looks like water but it isn't water, that mass ratio between hydrogen and oxygen is different. Like if you had hydrogen peroxide, for example, that mass ratio is 1:16. So what Proust showed was that atoms combine together in whole ratios, and that these things is what constitute some substances. Essentially what this means is that water is water because it has 2 hydrogens and 1 oxygen. If you take water from New York, water from France, water from the moons of Jupiter, and you analyze it, what you find out is that the proportion of the hydrogens and oxygen are constant. Once you change that proportion, then you don't have water anymore. John Dalton proposed the law of multiple proportion. He said that atoms combine in whole numbers, that these things, water and oxygen has 2 hydrogen and 1 oxygen, and that they combine in whole numbers. It's not 1 hydrogen and half an oxygen. It's 2 to 1, and that methane has 1 carbon and 4 hydrogens. It's not 1 hydrogen and a quarter carbon. So that was Dalton's law of multiple proportion. And Dalton sort of took all these laws that was proposed during the Enlightenment era, and he started to develop his atomic theory. It was a new philosophy of science that tried to give a better understanding of the atom. His proposal was that all matter is made out of atoms, that chemical reactions are neither, in a chemical reaction, matter is neither created or destroyed, simply rearranged. Atoms of the same element are identical, that is, a hydrogen atom in water and a hydrogen atom in methane are identical. You can interchange them. Compounds are formed from 2 or more atoms in whole number ratios. This particular postulate is a combination of Prowse's law and Dalton's law. So those were the postulates of the atom, and scientists or the society was gaining a better understanding of the atom. And the question was, well, yeah, we understand the atom, but what exactly is an atom? What is an atom made of? What are the parts that make up an atom? So there were still questions that were unanswered, like what is an atom? How is it put together? What are the parts of an atom? And so for the next, say, 200 years, scientists started to gain a better understanding of the atom. And this is just a schematic of what scientists have done in that time frame to kind of have to give us a better understanding that an atom has a nucleus, that the nucleus has protons and neutrons. Protons are positively charged, and that the volume, the size of an atom, is determined by its electron. So this just kind of gives you an outline of key individuals and their contributions to the modern atomic theory. And some of these key individuals are Michael Faraday. He actually discovered or realized that matter contained negative charges, and so matter had negative charge embedded in them. John Thomson gave us a better understanding of the atom and said that atom is kind of like a chocolate chip muffin, in that it's mostly a positive sphere, but it's embedded with negative electrons. And this was called the plum pudding model, because plum pudding, of course, was more popular back then than muffins, but you get the idea. Roger Millikan did an oil drop experiment in which he was able to determine the charge and mass of an electron. So again, in the 19th century and the beginning of the 20th century, the scientists, individuals, started to gain better, have a better understanding of the atom. And a guy by the name of Ernest Rutherford gave us our first concrete idea of the structure of the atom. He started with the gold thin foil experiment. The experiment basically showed that if you take some radiation and bombard a very thin gold foil with that radiation, then that radiation will pretty much go through that gold tin foil, because if an atom, as Thomson proposed, is mostly empty space with a few electrons, then the radiation should just go past the gold foil undisturbed, maybe a few minor deflection. So when Rutherford did this experiment, he noticed the pattern of the deflection of the radiation as it hit the gold tin foil, but he also discovered that some of the radiation bounced directly back, and so that gave he had to change his mentor's model of the atom. The plum pudding model had to be revised because this experiment showed that was not consistent with the result. And so, based on Rutherford's experiment, he said that an atom is mostly empty space with a very, very dense nucleus in the center. In fact, the mass of the atom is in the nucleus, and that the size of a pea, if you could take the nucleus of all the atoms and have it the size of the pea, it would be about 250 million tons.
The atom, so small it's hard to imagine. 72 quintillion of them fit into a single grain of sand. Finding out what an atom was made of led to our next great discovery. To get the story, I went to Fermilab outside Chicago and met with physicist John Wormersley.
Even 100 years ago, people knew how big the atom was, and they thought that electrons and protons would be spread pretty much uniformly throughout the atom. And they called this the plum pudding model because they thought of the electrons like raisins in a fruitcake, spread throughout the inside of the fruitcake.
In the early 1900s, physicist Ernest Rutherford conducted an experiment to further explore the structure of the atom. He shot radioactive alpha particles at a sheet of gold foil.
And he wanted to see what would happen when the alpha particles hit the gold. He didn't expect very much would happen. He thought most of the alpha particles would carry straight on through without being deflected, without being bent through any large angle. But what happened? Well, he found something completely different. He said it was as surprising as if you shot a 15-inch artillery shell at a piece of tissue paper and had the artillery shell bounce back at you. Some of these alpha particles bounce straight back off the gold foil. So the only way this could happen is if inside the atom is a very small, dense concentration of matter. It's not spread out like the plum pudding. And Rutherford called this small, dense concentration the nucleus.
So that was the discovery that showed that it's basically the dense nuclear model of the atom. So what are the parts of the atom? Well, the parts of the atoms are the following. It has an electron. Its mass is 9.109 times 10 to the minus 31 kilogram. That's really small, and its charge is 1.602 times 10 to the minus 19 coulomb. Proton is just the opposite of an electron in terms of charge. It's positive 1.602 times 10 to the minus 19. Remember, positive instead of negative, but it's much more massive than an electron. Its mass is 1.673 times 10 to the minus 27 kilogram. In fact, you need 1,837 electrons, 1,837 electrons to equal the mass of a proton. The last particle in an atom is the neutron. It's about the same mass as a proton, 1.675 times 10 minus 27, and its relative mass is also 1 AMU. We measure atomic mass unit in terms of AMU. That's what AMU stands for. And so these are the parts of the atoms. How they are, how they're arranged in an atom is the next series of experiment that we will see in the next chapter. But these were the models of the atoms that was proposed in the 1800s and the early 1900s. Dalton gave us our first concept of the atom, that it was made out of atoms. It was made out of small individual particles that couldn't be divided any further. Thomson gave us the plum pudding model, in that atoms are basically positive sphere with negatively charged electrons embedded in them. Rutherford gave us the dense nucleus model of the atom, where the center of the atom is where the mass is found. It's the most dense part, and the electrons hover around that nucleus. And then two individuals that we're going to be studying in the next section is Bohr and Schrödinger. Bohr gave us the planetary model of the atom, and Schrödinger gave us the wave duality, that electrons can't be explained as a particle, it has to be explained as a wave. So these are the models that led to the atomic theory. But really, when you think about it, theories always change, just like we described back in chapter 1. And so the atom is really more detailed than what we present here. And there are theories out there that says that when you go past protons, electrons, and neutrons, you get to quarks. And when you get past quarks, you get into even smaller subatomic particles. And that eventually you get to something called strings. And these strings are what is responsible for everything that we see. And so that is actually the proposal by scientists these days. It's called string theory. And string theory is a pretty radical theory out there. It proposes 11 dimension. It proposes that you can be here and there at the same time. So if you have the chance, go to the lecture notes and look at the YouTube series on string theory, and you'll be pretty fascinated about the 11 dimensions, parallel universe, and what scientists are really struggling with in trying to bring together a unified theory of everything about matter.